Welcome back to AP Calculus BC on that downhill side of things. We started our fourth topic last class, and that was mentioned. It will be split into smaller subtopics: parametric equations, vector-valued functions, and polar equations. This is actually our last day on parametric equations. They're kind of a weird side note in AP Calculus, and although they definitely fit in with vector-valued functions that we'll do next, they really are kind of skimmed over pretty quickly. And if we had more time, I'd love to go more in depth, but sadly we don't, as with many fascinating facets of math. But hopefully I do it justice over these couple pages of notes. So there are three pieces we need to cover about parametric curves. The first is how to find the length of a curve defined parametrically. The second is how to find the first derivative, dy dx, of a parametrically defined curve. And the last is how to find the second derivative of a parametrically defined curve. Let's start with the easy one. In the first semester, we defined arc length of a given curve f of x over an interval. So if we wanted to find how long a piece of a graph was, and we called that the arc length, and it was a very weird kind of standalone formula that we did at the very beginning of the semester, and now we're coming back to it. I like to split it into two pieces just so you see it twice instead of just one time. But anyways, we define that as we say we do the integral from a to b of the square root, and then this came from the Pythagorean theorem. If you might remember the derivation 1 plus f prime of x squared dx. And that is a formula that you still need to retain in your memory. Now, the advantage of having seen that once is it's not going to shock you to go one extra step and find the arc length of a parametrically defined curve. We derived this by using the Pythagorean theorem, and it was something along the lines of we had a curve up here, and then we talked about how a small change here, that was not great, but a small change here and another change over here, you could use the Pythagorean theorem and find that piece. However, it was a little bit weird with that f prime, and it actually, to me, makes a little bit more sense to do this parametrically, because now we know how something is going to change down here over time, and we know how something is going to change up here over time. And so our new arc length formula, very similar to the other one, is from a to b, but now is going to be, and I should make this square root a little bit larger, is going to be dx dt squared plus dy dt squared dt. Instead of having to do with just squaring one piece, and it might actually help you to think of this one being squared over here, now we're splitting the derivative into two individual changes, and we're saying, well, if we take the derivative of the x component and square it, add it to the derivative of the y component, square it, and then take the square root, that will find, through the Pythagorean theorem, the hypotenuse, which will be the length of our curve. So these two boxed formulas do need to be memorized. The one in purple is used for a typical y equals f of x function, while the one in red is used for a parametrically defined function. We'll see an example of this on the next page. There's nothing too much to do. I think life is much more interesting when we turn it to the first and second derivative. So the first derivative and the second derivative especially is really where parametric curves get a little bit strange. So we need to remember that dy dx discusses the slope of an equation, and in particular it really discusses the slope found between 2 points that are infinitely close together. And so we really should think of this as the slope formula, where dy is technically known as the differential of y, and it's the infinitely small rate of change of y. So if you have 2 points infinitely close together, it's finding the rate, or it's finding how the y values change between those. And then we divide it by the infinitesimally small change in x, the differential of x. So to find this with a set of parametric equations, we're still going to look at the ratio of the change of y over the change of x, but because our equation is defined with regards to t, we actually take the y component and we want to see how that component changes, but not with respect to x. Now we're going to see how the y component changes as you push t a certain amount. when you compare it to the x component as you push t that same amount. And by doing that, it will give you a very similar, in fact, the same answer as dy dx. And so the formula we need to remember is that dy dx, or the derivative of an equation defined parametrically, is given like this. Okay? This first derivative will be a function of t. So maybe it would help you to think of this as dy dx of an input t. And so if you are asked to find the dy dx, right, or the slope of a function that is defined parametrically, it shouldn't shock you that your parametric derivative will be a function of t as well. So I have a quick problem done here for you, and I've already done all the work, sorry to deprive you of it, but it's nothing too crazy. So we're given two parametric equations, or a parametric function, or a parametric equation, third tries the charm, an equation defined parametrically where the x component is here and the y component is here, and we're asked to find dy dx. Very easy to do. The first thing we're going to have to do is realize that we're working towards this ratio, dy dt divided by dx dt. To find dy dt, we just do d dt of y. What is y? Well, we have the equation for y up here, so we just do d dt of this equation, and now this isn't even implicit, it's all the correct variable, and so the derivative of 3t squared minus 2t, very easy, 6t minus 2. Like so. Same thing for dx dt. We do d dt of the x component, and our x component is hanging out up here. Okay, we need to practice that derivative, but we know t is to the 1/2 power, so here is our derivative. And as we continue through, you can also simplify and end up with this guy. And technically, what I have boxed in blue is our final answer. However, I wanted to remind you that we can, of course, bring this up to the top and distribute it inside to end up with a slightly nicer fraction that doesn't have any negative exponents. But it's ultimately up to you. You could have stopped earlier. So at this point, we are to a couple practice problems, no calculator here. And these practice problems, although they're labeled A, B, and C, they probably should be labeled 1, 2, and 3 because they don't really have much to do with each other. So what I like to do is actually work through these problems. And as we do each one, we're going to do A and then look at a graphical representation so that we don't lose sight of what we're doing with this. It's very easy when we start to get to these abstract, weird equations to forget that there is a graphical view of our answer. So let's begin. Given the parametric equations x equals stuff and y equals other stuff, write an equation of the tangent line in the form of y equals f of x to the curve at the point when t equals 3 pi over 4. Now here's the key thing. They're telling us that they want our tangent line to only have y's and x's in it. And that's a little bit weird until you think about what a tangent line is, right? Our tangent line, I'll call it t of x instead of f of x, is going to be a slope, of course, times x minus some value plus another value. So there's only values in here, so this function already is a function of x just by definition of how we've always done a tangent line. Now, how do we fill in these extra gaps? Well, that's a good question. I probably should have done this up above. I think also using t of x here is probably a poor idea because we're talking about t over here and those might get confused. So let's just go old school and call it f of x. Well, we know we need a derivative, that's dy dx, and we know we need to evaluate it at something to get a number for our slope. Now, at what do we evaluate it? Are we plugging in an x or a y here? Well, no, because this is a parametrically defined equation, we're actually going to evaluate this at our time of 3 pi over 4. And then it's going to be x minus, well, what x value? We don't know the x value. We need to take this x function here, and we need to evaluate the x function at 3 pi over 4, right? This is a function of t. Okay? And then at the end, we need to add on the y function defined at 3 pi over 4. And I know this is messy with all the extra parentheses, but I think it'll make sense in just a quick second. Let's start with the x and the y function. We'll start with x. So we know that x, and I'm going to change this to function notation and call it x of t is equal to 4 times cosine of t, which means then if I would like to find x of 3 pi over 4, then we just replace t with 3 pi over 4. That puts us in the second quadrant, and 3 pi over 4 cosine is the x, and in the second quadrant x is negative, so I think we get 4 times negative square root of 2 over 2. These reduce, this becomes a 2, and I'm looking at negative 2 root 2. Nifty. Then we, of course, have our y of 3 pi over 4. I think this is going to be pretty similar. We know that y is 3 sine of t, and so y of 3 pi over 4 becomes 3 times sine of 3 pi over 4. Sine is the y is positive in the second quadrant, so positive root 2 over 2, and so we end up with 3 root 2 over 2. So we've already determined these two ending values. Now we just need the derivative. Oof, that one takes a little bit longer, but it's nothing too bad, right? Because we need to remember, of course, that our derivative, dy dx, is going to be the ratio of dy dt divided by dx dt. dy dt, I'll switch back, we did y in yellow, is just the derivative of y with respect to t. So the derivative of y will be 3 instead of sine. The derivative is cosine of t. Easy enough. And then we need dx dt, which I did in purple earlier. So the derivative of this will be, don't forget, the negative 4 sine of t. Nice. I think from here we need to evaluate, and we can use that Leibniz notation where we put that bar. We need to evaluate at a time of 3 pi over 4. And luckily, we've already done most of this evaluation, so I'm actually going to skip through. We know that cosine of 3 pi over 4, we did that earlier, didn't we? That's negative root 2 over 2. And we also know that sine of 3 pi over 4 is positive root 2 over 2. I think we can clean this up at least a little bit. We're looking at negative 3 root 2 over 2 times, and then we saw that this one reduced to 2. Let's put that over 1, so we use the reciprocal. 1 over 2 root 2. Root 2's cancel, and I think I lost a negative somewhere. I did. There it is. And then our negatives cancel, and it looks like we just end up with a slope of 3/4, or a derivative of 3/4. Exciting. Now we have our final function, which shockingly came out very nice. We have a slope of 3/4 times x minus, that becomes a positive, 2 root 2, plus 3 root 2 over 2. So definitely a little bit more work than a normal tangent line, but nothing too awful. I think we should probably see if we did it right, and maybe the easiest way to see if we did it right is to graph. So I already have this original function graphed, and we saw yesterday when you have cosine and sine on a parametric function, you'd expect some sort of circle or ellipse, and when I get this graph up here, you'll see that it is a circle, or rather an ellipse. Nothing too bad. But we want to check that tangent line. In particular, they asked us where t equals 3 pi over 4. How do we see where that point is? Well, we just say 4 times the cosine of 3 pi over 4. Don't need that. Comma 3 sine of 3 pi over 4. Okay, so we can see the point out there, right? Now, don't want to do that. Now we want to write a tangent line to it, but we just did that. We saw that the slope was 3/4. It became x plus 2 square roots of 2. And then we needed to, I think, shift it, didn't we? Yeah, we needed to go up 3. I'm going to do the fraction 3 square root of 2 over 2. And look at that. That is an extremely good tangent line. Passes right through. Looks wonderful. Yay us. 1 problem down, 2 to go. All right, second problem actually goes faster. The second problem asks us to find all points of horizontal and vertical tangency given these parametric equations. Well, horizontal and vertical tangency is determined by slope. So let's start with our dy dx. Okay, so we need to find d dt of y and divide that by d dt of x. d dt of y, easy derivative, that is just 2t minus 3. d dt of x, also a fairly straightforward derivative, 2t plus 1. There's our slope. Now, two things have to happen in order to create either a horizontal or a vertical tangency. In order to create a horizontal tangency, and let's divvy this up, so let's do horizontal over here, that is when the derivative becomes 0, because we know that lines with a slope of 0 are horizontal lines. So what causes a slope to become 0? Well, that's if you're looking at a fraction, if the numerator becomes 0. So basically, 2t minus 3 must equal 0, which means that t equals 3 halves. However, they asked us to find all points in x comma y notation. So we know t is 3 halves, but how do we find the point? Well, we have nice equations up here that convert x's and y's, or t's, into x's and y's. So if I wanted the point, and I'll just kind of do it like this, a little sloppy but nothing bad, the x-coordinate will be 3 halves squared plus 3 halves, and the y-coordinate will be 3 halves squared minus 3 times 3 halves plus 5. And don't tell anyone, but I'm going to be really lazy and I'm not going to go any further. So, shh. Let's look at the vertical points of tangency. Vertical tangent lines occur when the slope is undefined, usually because our slope is approaching infinity or negative infinity. For a fraction to have an undefined slope, the denominator needs to become 0. So what causes 2t plus 1 to equal 0? Well, hopefully you all yelled and jumped for joy and said that t is negative 1/2. Same thing as before then. If I wanted those points, then I would have to take that negative 1/2, square it, and add it to negative 1/2. And same thing over here. Negative 1/2 squared minus 3 times negative 1/2, and then add 5. Lovely. Well, did we do it correctly? I hope so, but let's find out. The first thing we're going to do is look at this function, and I say function, it's not a function. It was actually a pretty fascinating graph. When I first graphed it, I'm going to get rid of these 3 guys so we don't cluster up everything. When I first graphed this, I just had it going from 0 to 1. That's what Desmos defaults to. And I was like, that's kind of a weird graph. And so then I started increasing this. I usually go to 2 pi. I'm like, maybe it makes a circle. But it didn't. And then I was kind of suspect. It's very weird that it would stop right here, because we don't have anything that breaks our function. So then I said, oh, I bet we have to go negative. So then I went negative 2 pi and said, ooh, now it's starting to curve. And then I got a little suspect. And I'm like, well, does it keep curving? It doesn't. It just kind of comes in and goes out at that oblique angle. So looking at this, I feel like there are 2 places where there are either horizontal or vertical tangencies. It looks like this guy right here, straight up and down, would be a point of vertical tangency, and this guy over here looks like horizontal tangency. And we're going to check this in 2 different ways. The first way is the easy way. We're going to take those time values, time of 3 halves and time of negative 1/2. And so I'm going to take that time of 3 halves. We're going to go 3 halves, and one day I'll learn how to use Desmos, but today is apparently not that day. There's the x-coordinate, comma, and then we'll do the y. So I'm just plugging 3 halves into the original equation up above. 3 halves squared minus 3 times 3 halves plus 5. Oh, look at that. That point right there looks pretty darn good to me. I bet a horizontal line would pass through this one perfectly. Go us. And then I'm just going to copy and paste the other, and now it's like, you did a new point. No, we didn't. We're just going to change this. We're going to use the other one, which was negative 1/2, if you remember. So I'm just going to change all of these to negative 1s, and we'll make sure that that's in the right spot. Always good to check your work, and of course you can do this on your calculator. Look at that. It looks to me like that point is perfectly on a vertical point of tangency. Now, if you wanted to check the x-y coordinates, you could, of course, do the math, and graph the point x comma y. But I'm pretty convinced we did it right since we already checked the time values. The rest is just, algebra. Really, it's not even algebra. It's just evaluating an expression. And so I really don't want to go through that. So I think that's pretty good so far. And now we are on to part C. Part C is actually the quickest of the 3 because they just want the setup of an integral expression. They don't actually want us to do any math beyond that. So they want us to give them the integral expression that will find the arc length of the curve given by these 2 parametric components. Well, we should probably remember what that looks like first. We're going from 0 to 1, and all we need to do is find dx dt, square that, and then dy dt, square that, and we're done. So finding each of those individually, dx dt over here, the derivative of x with respect to t is just 2t, and if we do dy dt, we end up with 12t squared. Nice. So finishing this off then, 0 to 1, we have this guy over here, and we'll leave the individual squares and the dt at the end. Our dy dt was 12t squared. Of course, order is not important. You're just adding two things together. So you could put dy dt first if that makes you happy, and this one here. And that's it. This is very, very common. We mentioned this first semester too when finding arc length. Anytime you throw something inside of a square root and you have some sort of exponent, it becomes pretty tricky to find the antiderivative by hand. So either this would be a calculator problem and they'd say, put this into your calculator and tell us the answer, or they would be just like this one is a very common free response question. Set it up, but do not evaluate. Of course, we are going to go a step further and see how we did here. So I'm going to get rid of all this cluster or clutter at the top, and we are going to look at the graph. So here is the graph of the parametrically defined curve from 0 to 1. It's this cute little guy down here. Look at this. Now, looking at this guy, it looks to me like it goes, if we wanted to find this, it's pretty close to a triangle, isn't it? Think of this as like the hypotenuse of a triangle. So if I wanted to find that, this would be over 1 and up 1, 2, 3, 4. Pythagorean theorem, right? Pythagorean theorem of a triangle would be over 1 squared and then up 4 squared, that's 17. So I'm estimating that if it was a triangle, it would be the square root of 17, which is 4.123. It's not a triangle, though, because it curves over. I think it's going to be a little bit bigger, maybe smaller than the triangle. I don't know. Yeah, a little bit bigger. And so, in fact, I have the actual value of the integral up here, which is 4.14. But you can see just by treating this as a straight line that we could get a pretty good approximation. But the exact length is that 4.1493. Nothing bad at all. All right, let's go ahead and move on to our last part of today, the second derivative. Now, the second derivative is a little bit trickier and conceptually tough compared to anything we've done so far. And ultimately, at the end of things, if you're like, I just want to memorize that formula, fine. It might come up. I think I've only seen the second derivative come up on an AP exam like once in 20 years. But it has come up, and it is fair game. So I think it's worth going through, and it does give a nice understanding of how derivatives work. But if this section seems a little too overwhelming, don't let it stress you out. Now, when we found the first derivative, we found the derivative of the function y with respect to t and divided that by dx dt. Now, the second derivative is similar to that because we are going to take the derivative of y with respect to t. But we're not really taking the derivative of y. We're going to take the derivative of y prime, or dy dx, if you will. And then we're going to divide it by dx dt. Okay? So what does that look like? Well, I'm actually going to give you the answer at the beginning and then explain what it means from here. So the second derivative of a parametric function is the first derivative, or rather the derivative of dy dx divided by dx dt. And that is a little bit weird because you might expect the second derivative, and I'm going to cross this off in a second because it's not right. So the first derivative, you're like, oh, we just did d dt of y, and then we did d dt of x, and that became dy dt divided by dx dt. So like that's the first derivative. Cool, we're awesome. Now let's find the second. You're like, oh, the second's going to be really easy. We're just going to do d dt of dy dt and then d dt of dx dt. That is not right. Instead, we are going to take our answer to the first derivative and take the derivative of that. And you're like, well, that's what I just said. And you're right, it kind of is. except then we're going to divide by dx dt, not ddt of dx dt, just by dx dt. And why are we doing that? Well, it's all about what it means, and so we're going to break it down one piece at a time. This numerator means see how the first derivative changes with respect to t. And that'd be pretty good. But we want to know how y changes with respect to x. And so if we just look to see how the first derivative changes with respect to t, that isn't giving us what the problem asked for. So what we need to do is also have the denominator which tells us the change in x with respect to t. And isn't that the second derivative, which measures the change in the first derivative as x changes? And again, conceptually, a little bit tricky. Now, math teachers and professors everywhere are going to cringe at this step, and I understand, but I think it is kind of fun, and it works with the first derivative too, so don't hate me too much, okay? I know it is kind of weird, but it should be okay. So what we're going to do is we're going to take this second derivative, and we're going to say, well, what if I want to get rid of this denominator? We've gotten rid of denominators before, and so what we do is we multiply the denominator by its reciprocal, by dt dx. And by doing that, these cancel and these cancel. Of course, we also need to multiply the numerator by dt dx as well. So what happens if we, this is the cringy part, if we multiply straight across? Well, is there anything we can cancel? I think so. Don't the dt's up here also cancel? And then we get d dy, which is d square y. And then multiplying these together is dx squared, which everyone just writes as dx squared. And isn't that the second derivative? Pretty wild there, right? So if we wanted to do a quick example, we already did example 1 with these exact same two functions. And in example 1, we found dy dx, which was down here. Now, if we want to find the second derivative, we need to take the derivative of dy dx with respect to t and divide by dx dt. So we take the first derivative, which is up here, and we do d dt of that, which results, of course, in this guy. Nothing too bad. You can follow the derivation process before. But then we also need to divide by dx dt. You actually had to find dx dt a lot earlier, so there's no extra math you need to do down here. Once you're here, if you'd like, you can perform that same trick, move it up, make the exponent positive, and distribute it inside, and it actually comes out to be a really nice second derivative. So that is all we need to know for our 3 parametric calculus connections. Arc length, and help me write it out, right? We go from a to b, square root of dx dt squared plus dy dt squared dt. The first derivative, so the first derivative is always defined as dy dx, and it's found by doing d dt of the y component divided by d dt of the x component. And then the second derivative, a little bit trickier. The second derivative, we need to find d dt of the first derivative, and we need to see how that changes when we divide it by dx dt. The next couple pages are just practice problems for you, and I think you'll find that they go pretty darn quickly for the first few. As always, I do have solutions worked out for you and posted on Teams if you need any help. As always, please let me know if I made any mistakes or there's anything I need to re-explain. Thank you for your time, and I'm excited to have you guys back for day 65.